In April 2020, astronomers detected an unusually bright and powerful radio signal never before recorded in our home galaxy. The source is a magnetar, a type of compact object with the strongest magnetic fields in the cosmos. Like pulsars and neutron stars, magnetars are the crushed cores left behind when a massive star explodes, but their super strong magnetic fields put them in a class by themselves. The fields are up to 1,000 times stronger than typical neutron stars, and over 10 trillion times stronger than a refrigerator magnet. They can rip molecules apart from thousands of miles away, distort the shapes of atoms, and store enormous amounts of energy. On April 27th, the magnetar, named SGR 1935, produced a rapid-fire storm of short, powerful X-ray bursts that lasted hours. The activity, first spotted by Swift, was also monitored by NASA's Fermi Gamma Ray Space Telescope and the NICER X-ray telescope on the International Space Station, along with other space missions. As the storm wound down early on April 28th, NICER recorded some 200 X-ray bursts in just 20 minutes. Later that day, SGR 1935 fired off another X-ray burst. This time, though, it was accompanied by something new, a powerful pulse of radio waves, lasting 1,000th of a second. CHIME, a radio telescope in British Columbia, led by several Canadian universities, discovered the signal and determined it came from the vicinity of SGR 1935. Another experiment, called Stair II, and operated by Caltech and NASA's Jet Propulsion Laboratory, saw an even brighter signal at different radio wavelengths. Since 2007, astronomers have been trying to understand the sources of powerful millisecond radio signals called fast radio bursts, seen from other galaxies. Magnetars have been prominent suspects. The duration and energy release of SGR 1935's radio signal is closer to fast radio bursts than any other source. For the first time, astronomers saw a magnetar in our own backyard produce a signal only previously seen in other galaxies. The discovery strengthens the case that magnetars are responsible for at least some fast radio bursts. Data from NICER and Fermi on X-ray bursts at the end of the storm showed that they differed from the one that coincided with the radio signal. This event's characteristics set it apart from the other eruptions, and further study may provide clues about how it also powered the radio burst. Radio waves from normal pulsars originate high above their surfaces. Exactly where and how, we don't know. A big eruption could launch a cloud of plasma to high enough that a radio burst could form. Never before have astronomers seen a fast radio burst so close to home. It's just one more reason to watch the skies and to keep tabs on the strongest magnets in the universe.